Hi guys, in this lecture of control systems we will talk about definition of 180-degree root locus and 0-degree or complementary root locus, and then we will be seeing certain sketching rules for root locus. Okay, before going to know how to plot a root locus, we will start with the definition of 180-degree root locus and 0-degree or complementary root locus. Our value s is equal to s1. S1 is a point in S-plane, and we want to know whether this is located on the root locus or not. S equal to S1 is on the 180-degree root locus. F and only F, 1 plus kg of S1 is equal to 0 for some real value of k. This means that if we take some positive value of k, then the point S1 in the S-plane, if we insert that point in the characteristic equation, it should result in 0. If it results in 0, we say that point S1 is located on 180-degree root locus. If it is not satisfying this condition, then we say that this point is not located on the root locus. Similarly, our value of S is equal to S1, which is certain point in the S-plane. If it is located on the complementary root locus, and when will that happen? If 1 plus kg of S1 is equal to 0 for some real value of k, which is negative. So for any negative k, if we can satisfy this condition for certain point S1 in the S-plane, we can say that this point is located on the 0-degree complementary root locus. Okay, mostly we will work with this 180-degree root locus, and we can extend those things or those principles or those rules that we derive to the complementary root locus. Also, we would see why we call it 180-degree root locus, and similarly we will also see why do we call it 0-degree root locus. So let's consider the characteristic equation that we were seeing so far, that is 1 plus kg of s equal to 0. So k is equal to minus 1 over g of s. From this equation I can write this thing very easily, and I know that this g of s is a complex thing, so I can always say that this is not only a single equation, it is actually two equations. The first equation can be written in the magnitude form with these vertical bars, meaning that we are talking about the magnitude only, and we are writing the magnitude separately in a separate equation. And this is 1 over g of s, this is one equation, and the angle of g of s is equal to angle of minus 1 over k, and I know that k is a real positive number. Since k is a real positive number, we can say that the angle of k is equal to 0. So angle of g of s is equal to 180-degree plus minus L into 360 degrees. Well, L is a factor that will determine the rotation of this angle. And why do we write this 180 degree? Because we have minus here. When we have a minus here, the angle of minus is actually represented by 180 degrees. In order to show that why this is 180 degree, we will consider 1 plus kg of s equals to 0. Since k is considered to be a positive number, we will have a plus sign here, and by simplification I can write kg of s is equal to minus 1, and further I can write g of s is equal to minus 1 over k. And now if k is a real positive, we can write this thing in polar form is 1 over k being the magnitude and angle of 180 degrees be the angle. Similarly, if k is negative, if this k is treated as negative, what will happen to this equation? This equation is then changing to something like this: 1 over minus 1 over k over negative k is eventually giving us plus 1 over k, and we can think that 1 over k is with angle of 0 degrees. Now from here this is evident that we have an angle of 180 degrees for k when k was a real positive number. So we had an angle of 180 degrees, and when k became negative real number we got an angle of 0 degrees. So that is why we normally call the root locus is 180 degree root locus and the other one is the 0 degree root locus or the complementary root locus. In the definition we discussed this thing that for every point we need to see that whether this is located on root locus or not. We have to put that point in this equation and find whether this equation is satisfied or not. If it is satisfied, we say that it is located on the root locus. If it is not satisfied for S1, then we say that the point S1 is not located on the root locus. If we have multiple points, then this job will become very difficult each time we evaluate this equation for each and every point. So what do we do? We will derive techniques so that we don't need to test every point on this plane. We have to derive techniques that are easily telling us that whether that particular point is located on the root locus or not. The angle criteria will tell us why the root locus is sometimes called the 180 degree root locus, as I discussed that in our previous slide. Now the key tool for any point on the S-plane, or that will tell us for any point on the S-plane whether it is located on the root locus or not, will be this formula. We will take the angle of g of s is summation of angle due to zeros minus summation of angles due to poles. So if we consider this formula, we will be able to find the angle of g of s. If the angle of g of s is equal to 180 degree, we will simply say that the point for which the angles were calculated is on the root locus. If this condition of the angle of g of s is not equal to 180 degree, we will simply conclude that that particular point is not on the root locus. So let's take an example. In this example, we have 1 0 and 2 poles. This is P1 and this is pole P2. Similarly, the 0 is located here, which is Z1. Now, suppose we want to measure, we want to take a test point here, S1. We are interested in knowing that whether this point is located on the root locus or not. Or alternatively, we are interested in knowing whether this point will be considered as a closed loop pole or not. So what do? We have to take angles. We have to take summation of angles of zeros minus summation of angles of poles. So we have only 1 0, so we will take theta z1. The angle due to this 0, which is a vector. If you plot a vector from here to this point, we will have an angle of, starting from here, that will be theta z1. Similarly, from this pole, the angle will be starting from here and measure up to here, that is theta p2. Similarly, the angle due to this pole will be starting from here up to this point. So this is theta p1. Now the formula is summation of angles due to zeros minus summation of angles due to poles should be equal to 180 degrees. And this is g of s1, theta of z1 minus theta p1 minus theta p2. If this results in 180 degrees or a factor of 180 degrees, then we can say that the point S1 is located on root locus, otherwise not. The question that comes to our mind is, where does this come from? If we look deeper into the complex number algebra, we can write this s minus z1 is a complex number into magnitude and its angle. The magnitude being s minus z1 with vertical bars and exponential of j angle of s minus z1. Similarly, this pole can be represented by its magnitude s minus p1 with vertical bars and its angle exponential of j s minus p1, and s minus p2 be represented by this s minus p2 with vertical bars being representing its magnitude, and exponential of j exponential of s minus p2 which represents its angle. 0 is represented by this vector. We have certain magnitude which is represented by the length of this arrow and certain angle which is given by this theta z1. We can shift this arrow here to the origin. and we have this theta p1 or this vector which has a certain magnitude, which is represented by the length of this arrow, and its angle is shown from this point to the point where it is ending. And similarly we can redraw this vector here, or for the second pole we have this green arrow, the length being representing its magnitude, and its angle is also shown. We are redrawing this vector here. Now what we are doing is writing all the magnitudes together. So some number divided by multiplication of two numbers is ultimately a number, and summation of exponential of j s minus z1, the angle due to 0, exponential of minus angle due to pole 1, and exponential of minus angle due to pole 2. And then we can further simplify and write this in this form, and we can see that angle of zeros minus angle of poles are there. So that is the reason that we were writing in our previous formula summation of angle of zeros minus summation of angle of poles. If this thing becomes equal to 180 degree, we will say that the test point is located on the root locus, otherwise it is not. And this is representing phase of g of s1. We can call this phase of g of s1, or you can say angle of g of s1. And now that angle of s minus z1 is theta z1, and angle of s1 minus p1, angle of pole 1 is represented by theta p1, and angle of pole p2 is represented by theta p2. This formula can be rewritten as angle of g of s1 is equal to theta z1 minus theta p1 minus theta p2. So now it's clear why we were writing this formula. Okay, another example. We have a test point S0 located here, and we have different poles. We have 4 different poles and 1 0, and we are interested in knowing that whether this point S0 is located on the root locus or not. So what do? We have to take the angles. We will have to draw vectors from all the poles and zeros and measure their angles. Suppose if we consider this 0 and we draw a vector from this 0 to the test point and we measure its angle, it becomes psi 1. This is psi 1. Psi 1 is the angle that is made by the vector that we plot from 0 to the test point. Similarly, for this pole, if we plot a vector which is joining this point, test point, and the pole, we will have certain angle that it will make with the x-axis or with the real axis. That angle is given a name phi 1. Similarly, for each and every pole, we will be writing its angle. And for this pole, we can see that the pole is having an angle of 0, because if we plot a vector, it is pointing in this direction towards the direction of S0. So the angle of this pole is 0. Now what do? We are writing summation. We are writing angles, summation of angles due to zeros minus summation of angles due to poles. So the formula will be g of S0. The angle of g of S0 will be psi 1, because there is no other 0. We have only one 0, so we will be writing psi 1 minus phi 1 minus phi 2 minus phi 3 minus phi 4. And this is how we determine that the angle of g of S0. Now if this angle is equal to 180 degree, we will say that this point is located on root locus. If it is not equal to 180 degree, we will say that this point is not located on the root locus. Now we want to discuss locus on the real axis. Suppose we consider a test point S1 on the real axis. We have located a test point on the real axis as shown. This is R of S, which means real of axis, and this vertical axis represents imaginary of S, which means imaginary axis, and this whole thing is S plane. And we have different poles located. We have this P1 located here on the real axis, Z1 which is 0 located on the real axis, P2 and P2 bar are actually complex pair of poles which are located as shown. Now we want to know whether that S1 is located on root locus or not. So we must consider, we must draw a vector from each and every pole and each 0 and measure its angle. The net angle should be equal to 180 degree if that point is to be located on the root locus. If that is not 180 degree, we will say that this point is not located on the root locus. So if the point is right of all poles and zeros of g of s, then g of s, angle of g of s is equal to 0. Why? Let's draw vectors from this pole. We have drawn a vector here, and from this pole we have drawn a vector here. Now the angle of this pole is this one, which is, let's say, phi 2, and the angle of this pole is exactly opposite, which is minus phi 2, or you can measure it from the other side. It will be 180 degree plus something, but I can write it minus phi 2 easily. Okay, the angle, if we draw a vector from this pole to the point, you will have this vector, and the angle of this vector is actually 0 degrees. So phi 1 is 0, and the angle of 0 from this 0, if we plot a vector, it is also having psi 1 equals to 0 degrees. So what happens is the net result will be psi 1 minus phi 1 minus phi 2 minus phi 2 bar. If we see, this results in 0 degrees. So what happens if such a case appears? Now this is the conclusion, that if the point is on the right of all poles and zeros of g of s, which is this case, this point is located to the right side of all the poles and zeros, then angle of g of s is equal to 0. So this is very easy too, because each time we don't need to draw these vectors and measure the angles, because this will be tedious for each and every point. So this is our very general rule, that if the point is located to the right of all zeros and poles, then the angle of g of s is equal to 0. And if such thing happens, this means that this point is not on the root locus. So because the angle should be equal to 180 degrees, since the angle is not equal to 180 degrees, so we say that this S1 is not located on the root locus. So we have an observation from the previous slide, that if the test point is on the real axis, complex conjugate roots have equal and opposite angles, which cancel and may be ignored. This is one of the observations that we discussed, because we drew the vector in our last slide that both the angles were cancelling one another. So if we have a point on the real axis, complex conjugate roots have equal and opposite angles, and they will always cancel, and they can be ignored. If the test point is to the left of one pole or 0, the angle will be minus 180 degree or plus 180 degree, so that the point is on the locus. Now if we have a case where the test point is located in such a way that it is to the left of one pole or one 0, the angle will be always be 180 degrees, and when such thing occurs, you will have to consider that that point is on the root locus, because it is satisfying our angle condition. Now let's consider this. If we have a test point to the left of one pole and one 0, which is shown here, this is pole and this is 0. So what will be the angle? We will plot a vector from this 0, and we see what is its angle. Its angle is 180 degrees. And now we will plot in a vector from this pole and see what is its angle. Its angle is also 180 degrees. So now angle of 180 degrees, summation of angles due to the zeros and angles due to the pole is minus 180 degrees. So this is going to be 0 degrees, you can say. So this point not on the root locus. This is not on the root locus. Now consider the second case, when we have two poles and the test point is located on the left side of two poles. So we will have again a vector from this pole. This is P2, let's say, and this is pole P1. Angle due to P2 is 180 degrees, and angle due to P2 is again 180 degrees. So what is the ratio is, since there is no 0, we will have summation of angle due to 0 is 0, and summation of the angle due to pole is 180 degrees minus 180 degrees. That means minus 360 degrees, okay, and which means that 0 degrees. 360 degrees also 0 degrees. So this point is also not on the root locus. Okay, now if we have third case, if the test point is located in the left hand side of two zeros, what's going to happen? You will draw a vector from this point. It is making an angle of 180 degrees, and similarly a vector from this 0 is also making an angle of 180 degrees. So by writing summation of angles psi 1 minus psi 2, psi 1 plus psi 2, summation of angles due to zeros, minus summation of angles due to poles. Since there is no pole, we will write 0, and psi 1 is 180 degrees and psi 2 is 180 degrees. So the net result is 360 degrees, which means that it is 0. So this point is also not on the root locus. So we will have a general rule from this, that all the points on the real axis to the left of an odd number of poles and zeros are part of the root locus. So all those test points which are located to the left of an odd number of zeros, poles and zeros are part of the root locus. If we have a point located to the left of an even number of poles and zeros, then that point or that test point is not on the root locus. If it is located to the left of an odd number of poles and zeros, then that is obviously located on the root locus. Let's consider this example where we have 3 poles only. One pole is located at the origin and the other poles are complex poles, as can be seen here. We are only concerned with the poles that are located on the real axis, because in our rule we only talked about the real axis poles. We said that the test point, if the test point is located on the left side of an odd number of poles located on the real axis, then that point is going to be on the root locus, otherwise it will not be on the root locus. Now in this case, if the test point is located here and we count from here that on the real axis we have only one pole and there is none other pole, so what is going to happen? We will consider that, and we can easily say that this point S1, if this is S point, this is not pole by the way, this point is located on root locus. Why? Because it is located on the left hand side of an odd number of pole on the real axis, and we have also seen that since these poles are complex, they will cancel the effect of one another. So we do not consider complex poles in this rule. We will only consider the poles that are located on the real axis. In this example, on the real axis we have only one pole located, so the left hand side, any point on the left hand side of it will be considered as on the root locus. So the shape of the root locus will be like this. We will have all this region, all this real axis beyond to the left of this pole located on the root locus. Let's talk about this example where we have 1 0 and one pole, and the 0 is located at -8. This is -8, and the pole is located at -1. Okay, now the rule was that we should have a test point which should be located to the left of an odd number of poles or zeros. So if we consider a test point here, if we take a test point here, then it is located to the left of even number of poles and zeros. So this point is clearly not on the root locus. If we consider any point between these two, or between this pole and this zero, any point, then it is obvious that it is on the left of an odd number of pole. So this each and every point between this 0 and pole will be on the root locus. So we can say that if we draw the segment, it will be like this. So this segment is completely on the root locus. This is the sketch of the root locus for this example, and this is it for today's lecture. I hope you will have liked it. Please put your questions in the comments, or you can ask me in the WhatsApp group. Thank you very much.